We will start with this problem. This is the first problem we are going to solve for heat exchanger. You will see the question here. It is a double pipe heat exchanger, shell and tube, like what you did during your lab experiment. And maybe you are preparing your lab report now, so definitely it will help you if you have some question. So this double pipe heat exchanger, you see, it is constructed with stainless steel, and we know the thermal conductivity. So if you look at the drawing at the bottom, you will see the inner diameter di and the outer diameter it is given. And so that's given di and d naught, and you see the outer shell of the inner diameter is 3.2 centimeters. So all information here given. Convection heat transfer coefficient, so as we have the inner pipe and the outer pipe, so then we will have the convection heat transfer coefficient for inner and outer side of the domain. So it's given H I equal 800 and H O equal 1200. So here, the fouling is another important aspect in heat exchanger. So we discussed during the lecture. So what I will do, I will not explain what is fouling, how it happens. So we only know the fouling factors here for the inner surface and the outer tube, the inner and the outer side of the tube. So that's the value given. What we need to do is we need to calculate the resistance, the thermal resistance. You all know how to calculate the thermal resistance. You did it in week 3. So thermal resistance of the heat exchanger for per unit length, so length it will be 1 here. We need to calculate the overall heat transfer coefficient for both inner and the outer surface of the tube. That means Ui and U naught. So we discussed during our lecture that actually the overall heat transfer coefficient U, and we derive the equations, the expression U equal, thermal resistance R equal 1 over UAS. So this is for the overall. And if you consider for the inner surface, then instead of U and A, you have to write UI AI for outer surface U naught A naught. We all know. So let's start with the solution. Look, this is actually the drawing here. So the hot fluid, it is actually going this way, and the cold fluid, it is coming from this way. So actually here, if we draw, this is the hot fluid. It is going through this stainless steel. This is the metal tube, the inner tube. This is hot. This hot fluid is going through the inner tube, and the material is steel. So this is the red color is the hot fluid, and you can see the color for the cold fluid. So maybe I can use that one here instead of black. So this is actually the cold fluid. Okay, so this is the cold fluid. Now you see, guys, here this is actually the inner surface. Okay, this is the inner surface, inner tube, and this is actually the outer tube. So when it is the outer one, the diameter is given d naught equal 1.9 centimeter, and the heat transfer coefficient is 1200 watt per meter square Kelvin, and the fouling factor, it is given 0.0001 so meter square Kelvin per watt. So that's actually the values given. Similarly, when it was the inner tube, inner surface, the inner diameter, di, it is given in the question 1.5 centimeter. Hence I, it is given 800 watt per meter square Kelvin, and the fouling factor, so here is 0.00001. So this fouling factor is eventually, this is actually the thermal resistance. So we need to calculate, if you want to solve this problem, initially it asks about the overall heat transfer coefficient for inner outer surface and the resistance. So if you guys know, I believe you all know these relations. from the formula. So maybe what we can do, we'll not write down any assumptions here. You all know that when we solve this sort of problem, so then we need to write some assumptions. So here actually what could happen, these fouling factors, okay, fouling factors and heat transfer coefficient in real case, it could change with the domain, with the length of the domain. So in this case we consider that, okay, the fouling factor and the heat transfer coefficient, it is constant, and that's correct. It is given in this question, the fouling factor and the heat transfer coefficient, that's constant. So you can write it is constant. So now when we will start with the analysis, so we actually need the thermal resistance R, and we know from the theory that R equal 1 over U A S. This is we know from the literature, we already discussed. It is the overall values. If we think about the inner surface of the tube, then we can say it is EY and AI. If it is for the outer surface, we can say U naught, A naught. So what we need to know, the first question is we need to calculate this R, okay, and the second question is we need to calculate this EY and U naught. So this is the second part of this problem, and this is the first part of this problem. So that means you can see from here it is kind of an expression with number of unknowns, 3 unknowns, but we only know the area and we can calculate the area easily. But then how we will calculate the resistance or the overall heat transfer coefficient if two values are unknown? So what do we know from previous weeks? Thermal resistance we can calculate different ways. So here, if you see, guys, if you can clearly see this is a double pipe, and you see the inner and outer tube from this drawing. If we enlarge this small section, let's say this section, then it will be something like, we can say, okay, this is the circle, that means the red circle. I'm now using the black one, and what it becomes like, this is the 5. If I say, yeah, this is this thickness, this one. So this is the the inner, and this is the outer part, okay, the outer section, the outer part. So according to this question, it's given that we have the fouling factors here at the inner and the outer pipe, okay. So we just enlarge this section, okay, the red circle, we just enlarge that section. So now if we draw the thermal resistance, look, it is actually this section, it is what fluid, it is cold fluid, okay, and this section, it is actually solid. This is the steel pipe, this is actually solid. Now it is fluid, so if I draw it like here, I think that will be much better. I can enlarge it like this. So this is actually the solid, and we got the fouling factor here at the inner surface and the outer surface. So I said this is inner, this is the outer surface, and it is hot fluid and it is cold fluid, okay. So according to the the heat transfer modes, this is fluid, and so that means here what will happen here in this section, it will be convection, okay, the heat transfer method, convection here as well. This one is the solid, so in this case we can say this is the conduction process, and we have the foulings. So if we draw the thermal resistance, so maybe it will be the first one, it is for convection, the second one, it is for fouling, the third one, this is the conduction, the fourth one, this is again the fouling, and the last one, this is convection. Try to connect it. Here it will be the hot fluid, this will be convection. Now this fouling here, this is the solid, so it will be conduction here. This fouling, it is again, and this cold fluid, it is the convection. So it will be the overall, this thermal circuit of this problem. So we know when it is the convection, the thermal resistance, we usually we can write it is 1 over what it is actually the inner surface. So we can say it is Hase A, so it will be Hase I AI, because this is the inner surface. Now for the fouling, this is actually the fouling for the inner tube. So we know the fouling is we can calculate the RFI, okay, over the area, okay. When it is the conduction for an annular tube, we know that the thermal resistance is the logarithmic ratio of the d naught and di, and 2 pi k L. Here this k, this is actually for thermal conductivity, so that's the conduction. This fouling, it is for the outer surface, so we can say RFO over A naught. And for the last one, the convection, this is for the outer surface, so it is Hase naught A naught. I believe you understand actually what I did here. So here the thermal resistance, that means the total thermal resistance R, it will be equal to this plus this plus this plus this. So that's the overall thermal resistance. So now what we don't know, guys, we don't know the area AI, we don't know the area A naught. That's the two values we don't know. And Hase I, Hase naught, it is given. You see, the Hase naught, RF naught, so all these values are given except the area. Now, now if we, just a second, here, okay, so if we calculate the area AI, it is circular one, so pi DIL. Pi is constant, DI it is 0.015, and L, the length is for unit length 1 meter, so it should be 0.0471 meter square. The area A naught for the outer domain is pi D naught L, so pi D naught, the outer diameter is 0.019 and length equal 1, so it is 0.0597 meter square. We got the area. So once we got this area, then what we can do is we can calculate the resistance. What we will do, we will substitute all of these values into the above relation. So Hase I, it is 800. I'm not writing the units, and the area is 0.0471. Okay. The fouling for the inner tube, it is given 0.0004, and the area 0.0471. Now the logarithmic ratio of the inner and the outer diameter, so the outer diameter is 0.019 over the inner diameter is 0.015 over 2 pi. Thermal conductivity, actually it is 15.1 and length L equal 1, plus now this one, the RFO, it is the fouling 0.0001, and area for outer domain is 0.0597, and finally the Hase naught, it is I think 1200, yes, and the outer heat transfer coefficient, and it is 0.0597. So it will be something like 0.02654 plus 0.00849. It will be 0.0025 plus 0.00168 plus 0.01396. So the total value will be 0.0532. So this is actually the local heat transfer coefficient, sorry, the resistance, the total the thermal resistance. What I got from here, so these two values, this one and this one, it is for fouling. Okay, those two values, it is for fouling, and this two values, it is, this resistance is for convection. Okay, it is for actually convection resistance. This is the convection resistance. So what we got from here, if we calculate it, maybe it is not important, but if you want to write down some discussion, then you can see this is the total value. So if we calculate the percentage, we found 90% of the resistance, it is actually due to the fouling. Okay, 90% of the resistance, it is due to the fouling, and only 5% of the resistance, it is due to the the conduction, the steel, the solid steel. Okay, and the rest, like this is 24, that means another 76% resistance, it is due to the convection. This is just for the discussion. If you calculate, okay, the percentage for, this is the total on, and then this, you see the rate too, it is for fouling. So calculate the total of these two value and then calculate the percentage. Maybe it is not important for you anyway. So now we did the first one, like the resistance. Now actually we need to calculate the local the values like EY and U naught. That means the overall heat transfer coefficient. So if we use this formula, R equal 1 over UIAI, so see, it will be R equal 1 over UIAI. So if we use this formula, then EUI, it will be 1 over RAI. So R dot resistance, this, so this is 1 over 0.0532, the resistance, this, and the area, 0.0471. So it will be 399 watt per meter square Kelvin. You need to do similar calculations for your heat exchanger report. So when we have done with this, then what we need to do, we need to calculate the values U naught. So similarly U naught, it will be 1 over RAO. So R is same, 0.0532, into the area A naught is 0.0597. So we'll get it 315 watt per meter square Kelvin. So that's all actually we have done with the solutions. So we calculated the inner diameter, we calculated the inner and the outer values for the overall heat transfer coefficient, especially for the inner tube and the outer tube, and we got it from the resistance, and finally we calculated the resistance. So that's it. The important part was whether you did the correct drawings for your thermal circuit or not. So you see here, I explained already. So that's actually the problem. I believe you understand clearly, and if you have any confusion, maybe we can discuss during the lecture again. So try to find out some similar problems